Hey there, and welcome. You've probably heard the term machine learning 1,000 times. It's the magic behind everything from your email to your favorite streaming service. But what does that even mean? For a machine to actually learn? Well, that's exactly what we're going to dig into today.
Right? It really is the central question. A machine doesn't have a childhood, it doesn't have life experiences like we do. So how in the world do we get a piece of code to look at data, get better on its own, and even start making predictions about the future? That's the puzzle we're going to solve.
Okay, so the most important part of this whole definition is that last phrase, without being explicitly programmed. Think about it this way. Instead of a programmer writing millions of lines of code for every single possibility, we just don't. We give the machine a whole bunch of data and let it figure out the patterns for itself. It builds its own little rule book to make decisions.
So this is basically our roadmap. It turns out there's more than one way to teach a machine. We're going to walk through the four main strategies: supervised learning, unsupervised, a little bit of semi-supervised, and my personal favorite, reinforcement learning.
All right, let's kick things off with the one that's probably the easiest to wrap your head around: supervised learning. The best analogy for this is just like a student learning with flashcards. You show the student a problem on the front, and then you show them the right answer on the back. You do this again and again and again until the student can see a new problem and guess the right answer.
Now, that answer key from our flashcards, in the machine learning world, we call that labeled data. Imagine you have a million pictures of animals. If every single one is tagged with a label, cat, dog, bird, the machine can start to learn what a cat looks like versus what a dog looks like. That's the heart of supervised learning. But, and this is a big but, creating all that perfectly labeled data, it can be a massive, super expensive job.
Okay, so inside supervised learning, the machine is usually doing one of two main jobs. The first is called classification. This is all about putting things into buckets. Is this email spam or not spam? Is this a picture of a cat or a dog? The second job is regression. This is all about predicting a number. Not if a house will sell, but for how much. What will the temperature be tomorrow? The output is a specific value.
And look, this is not some far-off futuristic concept. You are using this stuff every single day. That spam filter in your inbox, it was trained on millions of emails that were labeled spam or not spam. Your bank sends you a text about a weird purchase. That's a classification algorithm that's learned what your normal spending looks like. And it's even being used for incredibly important things like helping doctors analyze medical scans. All right, so that's all well and good, but what happens when you don't have an answer key? What if you've just got a gigantic, messy pile of data with no labels at all? Well, this is where the machine has to put on its detective hat and find the clues all by itself.
This brings us to unsupervised learning. We literally just hand the machine a data set and say, here, find something interesting. The machine's job is to sift through everything and find the natural groupings or hidden structures on its own. This is really powerful because maybe you don't know what the right answers are. The machine might find some really weird, surprising patterns you never even thought to look for.
So what's it actually doing in there? Well, it's usually one of two things. The first is clustering. This is just about grouping similar things together. A company could use this to find different types of customers based on what they buy. The other is association. This is about finding relationships, like noticing that people who buy hot dogs also tend to buy hot dog buns. That's a classic example, right? And then you've got this really clever middle ground, semi-supervised learning. Since labeling data is so expensive, what if you just labeled a few examples? This approach uses that small, perfect set of labeled data to help make sense of the giant, messy, unlabeled data set. It's a hugely practical shortcut when labeling everything is just impossible. Okay, now for what I think is the most dynamic type of learning. Let's forget about answer keys and messy data for a second. Instead, think about how you'd train a dog. You give it a treat for good behavior and maybe a firm no for bad behavior. That, in a nutshell, is the world of reinforcement learning.
So the key words here are agent and environment. The agent is our AI, and it's living in some kind of world or environment. It takes an action. The environment gives it feedback, either a reward or a penalty. The agent learns from that feedback and adjusts its strategy. And the goal here is super important. It's not just about getting the next reward. It's about getting the most possible reward over the long haul. It's playing the long game.
Okay, so let's walk through this. You've got our little robot agent. It looks at its environment and sees a fire and a water faucet. It decides to take an action. Maybe it moves towards the fire. Ouch! That's a penalty, minus 50 points. It instantly learns, okay, fire is bad, avoid that. It updates its strategy, and now it knows to try something else, like going for the water to get that reward. And believe me, this trial and error stuff, it's how we've built AIs that can absolutely crush the world's best players at insanely complex games like Go. It's also used to manage the energy in giant data centers, control sophisticated robots in factories, and it is a huge piece of the puzzle for teaching self-driving cars how to navigate our crazy roads.
So, we've talked a lot about the what, the different ways that machines can learn. But for a second, let's just peek under the hood and look at the how. How does a machine actually store all this knowledge? What does its brain look like?
Exactly. I mean, it's easy to say the machine learns, but what does that actually look like inside the computer? What's the structure that lets it connect all these dots and actually make sense of anything?
Well, it's probably no surprise that to build a learning machine, we looked at the best one out there, our own brains. On the left, you've got a real biological neuron, and on the right, you see the artificial version it inspired. By linking thousands or even millions of these simple artificial neurons together, you create what's called an artificial neural network, which is an incredibly powerful way to learn really complex patterns.
But, not every problem is just about spotting patterns. Sometimes a machine needs to think about cause and effect, to reason with uncertainty. For that, we can use something called a Bayesian network. You can just think of it as a little map of probabilities.
Let's just look at this simple example to see how it works. Okay, so a burglary or an earthquake could cause the alarm to go off, and the alarm going off could cause David or Sophia to call. Each of these connections has a probability. With this map, the machine can reason about what's happening. For instance, the machine can ask, okay, Sophia just called, so what's the new probability that there was a burglary? It's a really elegant way to handle an uncertain world.
Wow, okay, we have covered a ton of ground here, from simple flashcards all the way to mapping out cause and effect. So let's just pause for a second and boil it all down to the biggest takeaways. When you really strip it all away, it comes back to these three main strategies. You can supervise it and give it the answer key. You can just set it loose on your data and tell it to find something interesting. Or you can let it learn by trial and error from its own successes and failures. And which one you use just depends on your data and what you're trying to do.
And the big thing to remember is, this isn't science fiction anymore. These methods, all working together, are the engine behind the technology that is already changing our world in massive ways. Understanding them is kind of like understanding one of the most important forces of the 21st century.
And that kind of leaves us with one big final question, doesn't it? We are getting really, really good at teaching machines how to learn from data, how to learn from their mistakes. The question we have to start asking is, as this technology gets more and more powerful, what are the most important, the most helpful, and the most responsible things we should be teaching them next?